Okay, now, before we just go ahead and just run our very first feat for the Pareto method, important sampling, we have only one more step to take, and that one is that we just find an estimate for the number of the effective sample sizes. In order to do that, we essentially, and based on the things that we know about that, is that effective sample size is that because when you just run the chains on your the Markov chain Monte Carlo, there are somehow some kind of autocorrelations or anti-correlations, in a sense, correlations between the difference of the samples that you draw from, or should say, your posterior distributions from the parameters of space. Then these correlations, they have an impact on the inference when you're just going to have on the parameters that you're running your model for. Then as a result, we have to sometimes exclude the sample sizes that they are correlated. Then that's the result that the thing which is remained is called the effective sample size. Then now, in order to get that in our PSIS object, the thing is that normally we have to have a minus like likelihood of that object then when we just run the model then in order to do that, I'm just gonna, but before I just go to the minus the likelihood, let's go ahead and see the relative let me type it here, which I'm just gonna call that the relative, and you should have it comes here with the loop package. It says that EF, it's from the loop package, and it's going to be relative, I should say, let me press the F1, and you can see the menu which opens there as a help, but it helps you essentially to see what do we mean. You see that, for example, the thing which we have, it's effective sample size divided by the total sample sizes. Then essentially that's the thing that we just extract the samples which they have correlation between them and take them, I should say, as an effective sample size, but as a relative one, we divide those effective sample size divided by the total sample sizes which we have from the MCMC methods that we have had. In order to do that, there is a very easy method to do that. Normally we just have the exponents of this, and the thing which I'm just going to do, I'm just going to simply, just as an exponent, I'm just going to put these objects there, which I'm just going to call this as like woman. And sometimes when you run it, we can just also call that as NF, as an effective. But somehow when you run it, it asks, for example, sometimes the chain ID is not specified. You see that? We just get the error message that the chain ID is missing. And also when you just come to the help, you see that the chain ID is missing. In order to just put the chain ID, I'm just going to come here and I said that the chain ID. Normally the thing that we do, we just, because we initially run our MCMC methods in order to get the posterior distributions of our parameters of our interest, which they were our coefficients in our linear model, we just run our model based on the thing which has been, I should say, predefined in our model as StanGLM. Then the whole model was searching for the point of, I should say, the convergence in 4 different chains in parallel. Then because we had 4 chains, the thing that we do, we just say that we have 4 chains, 1 to 4. However, we are just going to repeat that from 1 to 4 because we had 4,000 samples. If you remember from the dimensions of the like woman A, the dimensions were 4,000. If we divide it by 4 chain, you get that each chain had 1,000 samples drawn and throws drawn from the posterior distribution. Then we said is that it's going to be chain 1 to 4. However, for each chain, each one is going to go ahead with 1,000, I should say, samples. Then I'm just going to go ahead to run this model. However, I had to just put another parenthesis. It seems that the model is going to be ready, and now I executed that by pressing Ctrl Enter, and now I have an object which is essentially a relative effective sample, which you see that we have that object created, and that thing, it shows a kind of a ratio of the effective sample size, which the correlated samples that have been removed from it, divided by the total, I should say, samples which we have thrown from our posterior distribution, either they were correlated or not, the total one. And now, however, if you are interested to see what kind of a class is an effective sample size, you can simply go ahead and see that, for example, that's the numerical one, and in terms of the dimensions that you want, you can just go ahead with the effective. You get that, for example, it's the dimension is going to be null because that's the numeric that you're working with. And then as a result, you do not get the dimension because the dimension is applicable to the objects which they are either a matrix or an array. If you have a numerical value, which is going to be an effective sample size, you have these numerical values, then you do not have the class, and then you do not have the dimensions of those ones, because as I said, the dimension is only relevant when you just want to talk about that in terms of a matrix or a data array that you have n, for example, by n matrix, and that's where you get the dimension. But in terms of the class, we saw that that's the numeric one, and also the other thing that we just wanted to do, as just right now we derived, I should say, the effective sample size, I should say, which is an object as a function, which is only from the loop package. We are just now ready to just run our fitting analysis. Now that we are just going to go ahead, have a Pareto distribution, fitted, I should say, to the lower upper parts of, I should say, our important sampling weights distribution, and extract and make an inference about the optimal values of the shape parameter in the Pareto distribution. Then from there, we're just going to move on to just find a method in order to compare to Bayesian methods which they have been fitted to our data system. Okay, at this stage, I'm just going to stop this tutorial, but when we come back, we are just going to do this fitting of the Pareto distribution to our important sampling weights distribution. Then I will see you on the next tutorial.